Anything else? Good to go? Okay, elimination reaction. Which mechanism does the leaving group leave in the rate determining step? Which mechanism does the leaving group leave in the rate determining step? Everybody good on that one? And which mechanism is the beta hydrogen extracted in the rate determining step? Everybody good on that one? Let's look at this reaction. You take this out to a bromide. This is tertiary butanol, tert-butanol, T-butanol, just heated in T-butanol, or no solvent at all. We can get this elimination product plus HBr. Mechanism. Importantly, do we have a strong base?
No.
Okay. A bimolecular reaction, SN2 or E2 requires strong nucleophile or strong base. No strong base here. In elimination, we call it a base because it takes an H. No strong base. So mechanism is what?
E1.
E1. Pretty straightforward. What's the first step of the mechanism? BR leaves. And we get carbocation. Which would be our rate determining step. We call this ionization, leaving group leaving. Carbocation. What can happen next? Plus what? Br minus? What happens next?
Oxygen takes away the hydrogen.
Well, you could, but that wouldn't show products that are formed. Hydride shift from here to here?
No.
Well, that would be just forming another secondary cation. Carbocations are prone to rearranging, but there's no rearrangement here. And if you did do a hydride shift from here to here, it'd be the same cation. Cation here and cation here is the same exact molecule. Oh, we just need to form a pi bond. What do we need to do? We need to remove an H. Okay? We can do the fast beta abstraction. What can take the H? By the way, before we do anything, how about if we rotate this bond here so these two can be anti? Right now they're syn. Which is better, syn or anti? Yeah. So here the bromine and the methyl are anti, but when the bromine's gone, these two groups are there. These two are probably going to want to rotate, and we get here. Thumb down, we'll rotate my arm, now thumb up. Now the Br minus, take an H, these electrons move in to make pi bond. What does that do? That gives product plus HBr, yeah? This is an E1 mechanism. Weak base. Or no base at all. You could do this with no salt, with nothing at all over here. If you just take this molecule and heat it, it may just eliminate HBr by this mechanism. And here the solvent really did nothing. That just acted as solvent. It could have acted as base. You could have had that act as the base instead. I mean, HBr may be ionizing the alcohol. It's possible that that could. But you could do this with no solvent at all. Formation of cation rate determining step, fast beta elimination here. Just like SN1, E1 involves a carbocation. Take this compound and heat it like about 300 or 400 degrees, you might start getting a gas coming out. The whole pH paper above it, it'll turn red. What is that gas? HBr being eliminated from the molecule. Summary statement at this point. E2 elimination requires what? Strong base. There's no strong base up here. That's why that was E1. It wasn't an elimination reaction, right? We're eliminating HBr. Yes. We've already covered thermodynamics and entropy for elimination reactions. Basically, it's the same as for SN1, SN2. Unimolecular or bimolecular. How many intermediates in the mechanism we did here? This is sort of unusual. You're usually not going to see a rotation in a mechanism. Since I did it, is this two different intermediates?
No.
It actually is, because they have different energies. All these have different energies? Anti-syn. It's like rotation. We did Newman projections, and we rotated 360 degrees around, and we showed energy levels. Yeah. Sort of the same molecule, but it can exist at two different energy levels. A syn and an anti. Again, showing a rotation in the mechanism is usually a little bit unusual, but I wanted to point it out because here the two groups are sort of syn on the single bond, but here they're anti, right, or trans. So how did that occur? It had to do some rotation. Can it rotate? Will it want to rotate? Yes and yes. It's going to want to rotate there. So that should all make sense. I think the handout somehow got out of order here. The next page is over here, there's E. Trying to figure out what's going on with this. I don't think any pages are missing. I just think one page is out of order. When regioisomers are possible. You may have heard that show, When Animals Attack. Well, this is when regioisomers are possible. If we take this compound here with the leaving group here and do a beta elimination reaction, we can only get one possible product. And it is, you're going to remove HCl and put in double bond between where the HCl was. So it's only one regioisomer, because the double bond can only be put in one region. It's also only one stereoisomer because this product is not stereogenic. Do you have sister trans here? No. So if you did an elimination up there, there's only one product to show. Unless it went by an SE1, which involves carbocation, and you start rearranging the carbocation. Is this going to be a E1? I don't even show a base. Can you do E1 with this alkyl chloride? What type of carbocation would you have to form? Primary, and would you form a primary cation?
No.
Or would you avoid those kind of like the plague? I would avoid primary cations unless there's a compelling reason. Down here, if you do a beta elimination reaction of this molecule, there's 3 possible products formed, theoretically. You could get double bond over here because there's a beta hydrogen here, and we could remove the HCl here and put the double bond in between where they were. But we also have a beta hydrogen over here. If that's his alpha, beta is that way, but beta is also this way. And we could remove HCl over here and put double bond over here. Let's call that HA and this HB. This comes from removing HA, right?
Mm-hmm.
This comes from removing HB. Well, what is that? These are just stereoisomers of each other. That also comes from removing HB. But if you remove HB, the resulting double bond can be either E or Z, cis or trans. This compound has no stereoisomer. Which product are we going to get over there? Well, that's what we're going to have to decide. Which alkene will be formed? It depends on a variety of factors, including mechanism, base, use, orientation of groups, and the starting material. First consideration, the most substituted alkene is the thermodynamic product. We already knew that. We talked about that at 10:20 one day a couple weeks ago. Yeah? In the context of elimination reactions, that is called the Zaitsev product. The thermodynamically most stable. Of the 3 up there, which one's the Zaitsev product? Of the 3, which one is it? First, second, or third?
Second.
Second? Yes, this is the Zaitsev product. Nobody knows how to spell Zaitsev. Some people spell it with an S, some people spell it with a Z. I think it's probably a Z. I think it's Russian. I think Zaitsev maybe worked with Markovnikov.
Zaitsev.
Is that right? Yeah?
Zaitsev, it's Russian, isn't it?
Yes. In the very late 1800s, there was some Russian chemist. That's the most stable of the 3 up there, yeah?
Mm-hmm.
2 reasons. What's the 2 reasons?
Trans.
It's most substituted. Disubstituted, that's only mono. But you got 2 disubstituted. How do you decide between them?
Cis and trans.
Cis and trans would help you there. The trans, okay, that's the Zaitsev up there. But this only talks about the most substituted. If you have 2 that are the same substituted, you can look at other things such as orientation of the group, cis or trans, yeah? Well, guess what? The Zaitsev product is always a major product in an E1 elimination. E1 always gives the most stable alkene possible. That's easy. But not in an E2 elimination, which can often give the less substituted alkene. Which of the 3 is the less substituted alkene?
First one.
Obviously the first one. In the context of elimination reactions, that's called the Hofmann product. HO1F 2Ns. Hofmann product. It depends on what mechanism you're doing. But if it's E1, we get which product? Zaitsev. Yes? That's what it says, right? Okay, look down here. If we take this alkyl bromide in water, probably going to have to heat this. The product is going to be as shown, that alkene. What's going on here? I thought I fixed that. I'm saying E isomer, not Z, but that's not stereogenic. What happened here? I thought it said like when possible. Does it say that somewhere? I don't know what happened here. Because the product shown is not stereogenic, right? So there is no E or Z. But if possible, we would get E. Because E is the most stable, and E1 is the most stable. Why is it E1? Weak base, there's no strong base. And in this mechanism, first step, ionization. Here, I'm showing what's taking the H, the beta hydrogen. Water take, okay, here. And we made HBr, but here with water, I showed it ionized with the water. Either way is possible. We could have showed it that same way in that tert-butanol reaction on the bottom of the previous page. You should know that mechanism there. So that's the product. Again, you got two beta hydrogens. You got a beta hydrogen here and a beta hydrogen here. But ultimately, which one is going to get abstracted? Here. But you want to put the double bond here. It would be more substituted there than here. You can show them both. The other product would have double bond here. E1 always gives the most stable product. Zaitsev. What about E2? E2, it varies. It depends on the base used and the orientation of the groups in the starting material. See, in E2, the base is involved in the rate determining step. And so the base has more influence. Same substrate as above, but here let's use hydroxide as a base, not just water. Hydroxide, strong base, yeah? It's going to be an E2, because we have a strong base, bully base, E2, here I come. And we take this beta hydrogen, inserted, electrons move in, leaving group gets kicked off, all concerted, and this gives what? Gives that. And it's the same product as above. Because it is the best product. And the better product is going to have the lower transition state leading to it, and indeed it is. But let's look below, and then we'll kind of compare these. If you use a different base, tert-butoxide, it will actually prefer to take this hydrogen and put the electrons in here and kick the bromine off, and the double bond will be down here, and that's actually called the Hofmann product. Why does this base take this H, but that base take this H? Very good. This is a more sterically hindered base. It's going to have trouble taking this H actually, because this H is kind of between two methyl groups. It's more buried. It's more sterically hindered. This H is more open. There's only one alkyl group there. This H is more accessible. The sterically hindered base has trouble taking this, so let's do something like that. No. Instead, it takes the more accessible H. And this is all because of transition state. This taking this H, the transition state energy is going to be high because the base has to kind of get in here just right. I got to work my way in there. And this is energy working, okay? Where the other H is boom, I'll just take this one then. Forget about you, I'll just take this one. Much easier. Forget about you, you're buried over here between these two alkyl groups. I'll just take you. Lower transition state. Does this give the best product though? No. But guess what? The reaction outcome is based on the transition state energy, not the final product energy. Right? This is like this. You don't need to draw this. What if we went from here to here? Or here? Okay? Which product is going to be formed? This is all energy. Which product is going to be formed? You don't know. It depends on what? Okay? Well, let's do this. Which product is going to be formed? A or B? A. A is easier to do. A is going to be formed. Unless you can establish an equilibrium. And this should be reminiscent of Diene reactions, 1, 2, 1, 4. You can't go backwards here. And so you cannot achieve an equilibrium here. And this is the pathway that's going to be easier. Taking the more accessible H is easier. Taking the buried H has a higher activation energy because there's sterics around it. And you actually get the less stable product.
Wouldn't the transition state energy be the lowest if the OH just took the less sterically hindered hydrogen? Why doesn't it do that?
Up here?
Yeah.
Why doesn't it take the less? Okay, good question.
Wouldn't it be the easiest? I mean, it's forming the best product by taking the hindered, but
Well,
wouldn't it be easier to take?
you're right, and I'd have to think about it if I really have a good answer, but here's the answer. And we haven't said this yet, and we need to say this. The answer is, because this is so small compared to this, apparently taking this H remains easy. Now you could say, but it can't be easier than this because that's more accessible. And that's where maybe I don't have an answer and I have to think about it because it's a pretty good question here. But what we're going to say is a small base has no trouble taking the more hindered H. And ultimately, what we can say is you're going to get this product. This is the product that's going to be formed unless you use a sterically hindered base. You start using this highly sterically hindered base, you're more prone to getting this product because the sterically hindered base has a better chance, or it's easier to take the more accessible H. Read what's here, think about it, and we'll see if we can discuss it a little bit later.
Yeah, but for the first example, since it's a stronger base, it can do that more easily than the sterically hindered because it's a weaker base in that terms of.
No, they're both kind of pretty darn strong bases because sterics doesn't affect base stream. So that's really not the right terminology. It's really sterics. Sterics makes it this more difficult, and so instead it does that. There's no sterics here, and so you take the H, which gives you the best product. But again, you could question that a little bit, and it's a real good question. Because you could still say, well, regardless, it still should be easier to take that. there's some fine details in here that we're not seeing maybe. Okay, let's, so this is an example of when you would not get the safe step product. Stair cleaner base actually tends to give the Hofmann product as the major product. Okay? So, with E2 it varies depending on base used. We are doing E2 down here, right? Because in both cases we have strong base. Strong base is going to be E2. It also depends on orientation of groups in the, this is going the other way, over here. Number 2, orientation of group. Stereochemical requirement for E2 elimination. In an E2 elimination, the leaving group in the beta hydrogen that is being extracted must be coplanar. With anti-coplanar, which is sometimes called anti-periplanar, very much preferred over syn-coplanar. These two fingers are syn-coplanar. They're both up, but they're in the plane of this plane here. Okay? How about now? Are they coplanar now? No. Syn-coplanar. Not coplanar at all. How about now? Now they're in this plane. Are they syn or anti? Anti-coplanar. They must be coplanar and anti-coplanar highly preferred. Did I say that syn-coplanar, can an elimination take place syn? Yes. But guess what? Anti is highly preferred. Syn is difficult, but it can happen. Okay, I did not say it could not. Different ways to show this. This would be anti-coplanar. Basically, if you consider the bond here, the bromine is this way and the H is this way. If they're all on the plane of the board, anti-coplanar, how can we show this a different way? Newman projections. Right, if you're looking, this is as if you're looking over here, right? Front carbon, bromine going straight up. Back carbon, H going straight down. Right? Okay? This would be anti-coplanar, shown in a Newman. Syn-coplanar. Syn-coplanar would be, the H would also be up and they would be eclipsed. Yeah? We can also see this on rings. Here the H and the Br are anti-coplanar. Bromine straight up in the board, H straight down in the board. Over here, I'm showing two beta hydrogens here, 2 beta hydrogens here, compared to the alpha carbon that the bromine is on. Are any of those H's coplanar to the bromine? The answer is no. None of the 4 are coplanar to the bromine. That gives us a take-home. The leading group must be axial to be coplanar to a beta hydrogen. So here the bromine is axial. And that H is straight down, the bromine is straight up. Here the bromine is this way. Do we have an H that way? No. We also don't have an H directly this way. None of these H's are coplanar. When the leaving group is equatorial, none of the beta hydrogens can be coplanar. Thus, when the elimination takes place, the bromine has to be what? Axial or equatorial? It has to be axial. If it's equatorial, it cannot eliminate because none of the H's are coplanar, especially anti-coplanar. Okay? So we need to understand rings. Here we go. Let's consider the red a leaving group. Right now, is it axial or equatorial? Axial, straight up. Look at this H over here, white. It's straight down. Okay, they're anti. Are they coplanar? Look, if I hold a piece of paper up here, they're both in the plane here. Straight up, straight down. They're anti-coplanar. By the way, if this was an H over here, it would also be anti-coplanar. Both of these are. Because if that was an H coming down, it would be like this. Let's do a ring flip. Now the leaving group is equatorial. Is the H over here, or any of these, is either one of these coplanar? Actually, no, because if you look through there, in this plane, the bromine is on this plane, but the leaving group is coming, if the plane is straight back through there, this is coming out this way. Both of them are. Over here, neither one is. Okay? If the leaving group is equatorial, neither one of the neighboring H's, in this case, neither of the four, it's what we said up here. The leaving group has to be axial, and when it is, a neighboring H can be anticoplanar. This is a stereochemical requirement of the E2. So if you're doing an E2, you got to keep this in mind. Here we go. Here's a reaction. Here, KOH, which we're using today in lab, yeah. And isopropanol. We've used that to recrystallize before. We use as a reaction solvent. Probably heat. Usually E2 always requires a little heat. Not always, but usually. Show expected product. Okay, first off, do we expect Zaitsev or Hofmann product? Zaitsev or Hofmann? What type of base are we using? Is the base sterically hindered? No, hydroxide. That's the least sterically hindered base around. It's very small. Most other bases are going to be bulkier. So, is it going to have any issue forming the Zaitsev? No, we should be able to get the Zaitsev. Okay. Can you just show the Zaitsev product? Does the Zaitsev product have stereoisomers? It should. It should. Here we go. How about this question? This is a common question. How many products are theoretically possible here? How many beta elimination products are theoretically possible? Like above, we showed 3, and ultimately we said this one's going to be formed. Well, it comes from how many different beta hydrogens do you have, types. There's a beta hydrogen here. We call that HA. Is there a beta hydrogen here? No. This is alpha. Beta, beta, no H there. Beta, H here. It's going back, yeah? We'll call it HB. If we remove HA, what will the product look like? Well, double bond will be between this carbon and this carbon, right? And we'll have an alkene. What else is on the N carbon? 2 H's, that's it. 2 remaining H's. What's on this carbon? A tert-butyl group and this group with there. If we remove HA, we'll get that product. Everybody agree? That's removing HBr, but removing HA. And we would call that the what product in this reaction? That'd be the Hofmann product. Is it stereogenic?
No.
Not stereogenic. We don't have to worry about stereoisomers there. That's it. If we were using a highly sterically hindered base, that would be our product. We're not. We have a very small base. It's going to take HB and give us the Sate product. What will that? We'll put double bond between these two carbons, yeah? And so here, this carbon has a what? A methyl and a T-butyl. Methyl and a T-butyl. And this carbon has a what? Ethyl and a methyl. Ethyl and a methyl. Yeah? But that's stereogenic. Because the double bond, we could also have, here the methyls are trans, we could have the methyl cis. This is the same alkene, it's a stereochemistry. Same meaning that both of these come from removing HB. But which product are we going to get? Both of these can be called Sate. But you actually only get one of these. Which one do we get?
Trans.
One on the right?
Right.
Yeah, one on the left with the metals.
Why do you say the one on the right?
Because that's the way it was oriented.
Because that's the way what is oriented.
The original.
Yeah, but it can rotate though. I mean, everything here can rotate. It's all sigma bonds. Are you recognizing it can rotate? Somebody else?
Beta H.
Somebody said the one over here? Well, let's get to it. What do we know about the requirement for the HB and bromine? They have to be what? Coplanar. What's highly preferred? Anti-coplanar. Some people will go ahead and say they have to be anti-coplanar. But again, syn does work, but you're only going to do syn when you can't do anti. And some people will tell you never do syn. But we'll get to that maybe later. We've got to make sure that the H and the bromine, let's get rid of that one. We're eliminating this H. Anti-coplanar. What's the best way to see that? Newman projection. Best way to see it. Let's draw this in a Newman. Okay? Let's stand over here. We'll put this carbon in front. Let's get rid of this Hofmann here. Front carbon over here. What do we see coming straight down to my feet?
Right.
Methyl. I'm going to put that as an ME. What's coming out off the board to my right if I'm over here? Ethyl, correct? Coming off the board, bolded. Okay. If I'm over here to my right, ethyl. What's going back if I'm over here? Hydrogen. HB. Okay, let's look at the back carbon. What's going straight down on that back carbon? Terbutyl. It's actually eclipsing the methyl. We draw it just a little bit to the side, right? Those are actually eclipsing. What's on the back carbon going to my right if I'm over here? Methyl. It's actually eclipsing the ethyl. Those are supposed to be right in front of each other. If I'm over here, what's going back? Bromine. It's actually eclipsing here. And there's your HB and bromine. They're actually coplanar. They're right in front of each other. Okay? The HB and the Br are supposed to be eclipsing. They're right here. And here's the plane. You can lay a piece of paper on the two pins and that would be the plane. Okay? They're like this. Now on the board I drew them a little bit like this so we can see them. But they're actually, okay, yeah? Is that how it's going to eliminate or want to eliminate? No. This thing's going to rotate. You can rotate the front and the back. I'm going to rotate the front, and we want the HB to be over here. I'm rotating the front. The back is the same. We got bromine, methyl, and T-butyl. Is that right for the back? Same thing. Now the front, we want the HB to be here. That means the methyl is going to go where? Straight up, right? We're taking the front, and I'm rotating it here. What is that, 180 degrees? Everything's going opposite. Methyl's going to end up here, and what else is on the front? Ethyl will end up here. Going to rotate there. Now look at the H and the bromine, and they are what? Now they're anticoplanar. I indicated the plane with the circle there. Consider that just flat like a piece of paper through there. Here's the plane. That bromine is going that way, the anticoplanar. That's how it's going to prefer to eliminate. At this point, the base, I wouldn't draw this, but the base takes the H, the electrons move in. You can't see between the two carbons. The electrons move in between the two carbons and kick off the bromine. Anticoplanar. Importantly, your groups are there. Your methyls are on the same side. Okay? The methyls are on this one side. The other side of the plane is the T-butyl and the ethyl. Which product has the methyls on one side and the T-butyl and the ethyl on the other? I'm saying side, not end. This one. Methyls on the same side, T-butyl, ethyl on the other. This is your product. Because it's a concerted mechanism. Take this, electrons in, bromine off, all at the same time. The groups are in this configuration, and when the double bond is put in, now they're fixed. You said the one on the right. Do you agree it's the one on the left? One on the left. Because we understand the anticoplanar preference. That's how it eliminates. It's just one transition state. Groups don't have a chance to rotate. It's not going to eliminate here. The transition state here is way higher. It's much easier for it to rotate. Then it eliminates. And so this is Satesef product. But it's this stereoisomer. By the way, is this E or Z? The two big groups are on it's the same side. It actually is Z. That is this the best? Is this the best alkene? No, this alkene is actually better. So this is actually officially the Satesef product here. But the reaction gave this product, which is not actually the best. So is it Satesef or not? It's sort of halfway Satesef. It's a regioisomer of the Satesef. It is the more substituted. But it's not as good as that.
So if you were doing E1, it would have to be the one on the right. because
Good.
that would be the-
Good. Yes. E1 gives the best alkene possible. Yeah. This would be the E1 product here. Yes. But this is the E2 product. Because we're doing E2, right? And so this is a case where E2 does not give the absolute best alkene like E1 would. You can try the next below. THF is just a common solvent, tetrahydrofuran. Just a solvent. What about this base? You think that's sterically hindered? Got these huge wings on it. Very sterically hindered. But This is what I would do for practice. I would show both Hofmann and Zaitsev products. Or Zaitsev and Hofmann. Okay. However you want to spell Zaitsev. Show both Zaitsev and Hofmann products. Down here, rings. Anybody remember what TEA is? We saw it in the substitution handout. Triethylamine in the substitution handout. We said it was often used as a sterically hindered base. It's an sp3 amine, even though it's a neutral nitrogen. It is strong enough to do an E2. It is considered a strong base. Someone have a product here?
Don't use one of the hydrogens, right?
I would say that would be the product. E2? Why is that the product? Well, let's look at the H's. Let's call that one HA. There's two here. We draw them both in. HB. Everybody agree those are the H's? Now we would maybe love to put double bond in down here, because the double bond would have three substituents. It would be tri-substituted. But look at this H. Is this H anticoplanar to the iodine leaving group? Anti is synonymous with trans. These are cis. Can these become anticoplanar? This is a cyclohexane, chair conformation. The leaving group has to be in what position to eliminate? Axial or equatorial? Axial. Let's put it axial. Here's the iodine. Let's go next door. Ethyl. Is the ethyl axial or equatorial? If the iodine is axial, how's the ethyl? It's also axial, right? Everybody agree? If we put the H here, it's here. Put the H here, it's what? And that is HA. Everybody agree that these two are trans? They're supposed to be trans. They're trans here, right? Okay. Let's put these two H's over here. That's a straight down. And we have like that. The straight down is axial. Which one is straight down? HC, and this is HB. There you go. Which lettered H is anticoplanar to the iodine? Which one? A, B, or C? Do you see it? It's straight down, the iodine is straight up. Yes. This is the one, the base triethylamine takes this H, these electrons move in between there and kick off the leaving group. But when it does this, the transition state, the H that's being abstracted, the beta hydrogen that's being abstracted from the leaving group are anticoplanar, and that is highly preferred. Reason being, we didn't mention it before, is when these electrons move in, they're almost coming in directly behind the leaving group. Sort of like backside, which might sound familiar. See, if we took this H, the electrons would be coming in sort of side-side. These can come in backside, sort of analogous to that. Which H remains over here? If we had them labeled somehow, I mean, an H is an H, but if they could be, maybe if one was a deuterium or something, or I don't know. HB remains, and then of course HA is here. There's nothing that's down there. This remains tetrahedral. But this carbon is now trigonoplanar, and so we put that bond in the plane, yeah? Okay? So again, we would call this the Hofmann product. It's not the most substitute. Think about this down here while we take a 2-minute break. It could be, whatever the elimination product could be formed. That double bond could be there. But that carbon is no longer tetrahedral. And, no. Well, there'd be nothing there. What, that carbon has zinc. It's gone. Anybody have the answer? Which reaction would be faster? What do we really need to look here? What's really the question? Any questions about this over here for our basic? Really, the question here is, in which starting material would the iodine most likely be axial? And that's the one that's going to be faster. Let's draw a chair with the iodine axial for the first compound. Let's put the iodine axial. The T-butyl is 1,3. The T-butyl is, let's put it up here. Let's not worry about enantiomers. Okay. Is the T-butyl axial or equatorial? Also axial. This is A, yeah? The two groups are cis. So when the iodine is axial, the T-butyl is also axial. Let's do B. The iodine is axial. How's the T-butyl? Well, in B, they're trans, so this would be equatorial. Okay, if you want to draw the H's just for clarity. You see that there the two groups are trans. There the two groups are cis. Which compound is going to be mostly in this conformation? This is the conformation it can eliminate in. Are they both just as likely to be in this conformation? Or does one of them want to do a ring flip? A wants to do a ring flip.
It has 1, 3 diaxis.
Ring flip more likely. And when it does a ring flip, the iodine is now what? Equatorial. Well, guess what? It can't eliminate when it's equatorial. And majority of the time, it's in a conformation that can't eliminate. So is that going to be fast or slow to eliminate? It'll be slow. It can't eliminate it. This one, though, actually prefers this conformation. Why? Well, more than that one, but here the big T-butyl, now iodine is kind of big too, but I think T-butyl is bigger. T-butyl is kind of happy. This one's going to be more in the needed conformation. And so it should eliminate faster. Which one was it? B. B should eliminate faster. It's going to more often be in the right conformation. Everybody agree? So you have to understand chair conformations, and we discussed those. That was a prereq to this discussion. Also, if you look back at test 1 questions, there was a question in my workbook when you were doing vote and chair conformations, and it asked you about a beta hydrogen. Now, I had to explain the beta hydrogen. Page 9. If you look back at it, transdiaxial. That's another way to explain anticoplanar. I mean, the H that gets eliminated is either this one or that one. Put double bond in here or here. These are anticoplanar. We could also call these transdiaxial. They are trans, right? And they're both axial. So that's just other terminology you could use. I said this question has relevance to E2 elimination, which will be covered later. You can look back at that now. I don't know if you remember that when you first looked at it. What other elimination product can be formed in reaction A? Well, instead of removing the beta hydrogen here, we can remove one here. Now, one of those will be anticoplanar. And we could have also have put double bond there. Nothing would have changed over here. In this case, they're both di-substituted. So it would be a little bit difficult to determine which is best. Okay. Next. Is this next when we on E? Yeah, okay, when reader isomers are possible. All right, E. F, okay. All right, we're going to start kind of bringing back in substitution some. When either substitution or elimination is possible, which will occur, heat favors elimination due to entropy. Take this and heat it with water, we show an E1 product, and we've shown this before. And this is favored by entropy because if you get rid of water, or just ignore it, one molecule is being converted to how many? 2. And so that is that's favored by entropy. That's a favorable entropy term. And if we heat, that magnifies the favorable entropy term. And so that's going to make delta G better and better the more we heat. Compare that to substitution. When you do a substitution, this reacts with water, the water replaces the leaving group and we make HBr. Is that favored by HBr? 2 going to 2. So that's not any favorable entropy. And so heating that is not going to improve your delta G. Right? Temperature magnifies entropy. Number 2, involvement of a good nucleophile will favor substitution, while a poor nucleophile will typically favor elimination. If we take this alcohol and react it with HBr, we can get an SN1 reaction. And mechanism involves what? First step of this mechanism? Protonate the OH. Make it a good leaving group. Then it can leave and make carbocation. What type of carbocation is being made? Tertiary. And then the last step, Br minus attacks. Get this product. Or would it be SN2? Why am I saying SN1? Could it be SN2? Why not SN2, Julie? Right, the leaving group's on tertiary carbon. You don't do SN2 on tertiary carbon, right? Yeah, it's like an SN1. You got to protonate the OH first to make it a good leaving group. On the other hand, if you do this reaction with HF, you're probably going to get an E1 reaction. Now, in both cases, we protonate the OH, and it leaves, and it makes this cation. The difference is, up here, Br minus attacks the cation, and this is an overall substitution product. The Br has replaced the OH. It's because Br is a pretty good nucleophile. It likes to add to carbons. Down here, F minus is not a good nucleophile. Instead, F minus will prefer to act as a base, and to get that product, which H does it take? It takes one of these H's here, and these electrons move in. We get this product. We reform HF, and so it was called a catalyst in this reaction. And we essentially will eliminate water. We're essentially dehydrating this alcohol. We remove water. Water's gone. And HF was a catalyst for this reaction. See, F minus is a lousy nucleophile. It doesn't like to make bond to carbon, but it will act as a base. Remember when we use certain acids for alkene reactions? We use sulfuric and HF. We said that those would never attack. But we're saying the same thing here. But Cl minus, Br minus, and I minus will attack cation and give you a substitution product. So, good nucleophiles favor substitution, poor nucleophiles favor elimination. Poor nucleophile down here. I call that dehydration. Dehydration of an alcohol with sulfuric acid is very common. Or you can use HF, but this is much more common. And this mechanism is what? First off, it is an elimination. We're eliminating the H from here and the OH from there. Together, that's called water. Okay, we can show that sometimes like this. Water is being removed. The acid is actually a catalyst, H plus catalyst. What's the mechanism here? It is an elimination, right? We're eliminating water. E1 or E2? E1 or E2? Quick, who says E1? Okay, who says E2? Why is it not E2?
So
What?
you have to form a carbocation to make that OH group be a
No,
hydrate.
you don't have to form a carbocation.
The OH isn't a good leaving point.
Protonate it, but once you protonate it, you can then either do a backside attack and kick it off, or eliminate it, or you can make carbocation. It can be concerted, or it can be unimolecular or bimolecular. Yes, you have to protonate because OH is a terrible leaving group. Why is it not E2?
If you form a new catalyst, would it produce the same?
Should we look back in the handout? Why is it not E2? I don't know. Did we find it? Yeah? I was thinking it's probably in the handout. So, what does it require?
Strong base.
Okay, well, let's find the strong base. Okay, where's the strong base at? We're doing this in sulfuric acid. Where's the strong base? You can't have a strong base in sulfuric acid. It's like reaching into your cold ice water and, like, where's the hot water? There ain't no hot water there. It's cold water. All right? It's acidic conditions. You cannot have a strong base under acidic conditions. Everybody agree? Good. Okay. So it must be E1. It is indeed an E1. There's no strong base. It's a dehydration of alcohol by an E1. Very common way to make alkenes. It's a very common reaction of alcohols to dehydrate them by an E1 mechanism. All the steps. First step, protonate the OH. What's next? Then the positive oxygen leaves to make carbocation. It's the same steps as SN1. The only difference is the fate of the carbocation, just like up here. Nucleophile can attack carbocation, you get an overall substitution product, or you can remove an H and put in a double bond. That will be an elimination product. Do we have a good nucleophile here? What's the nucleophile possible here? Sulfate minus. Is that a good nucleophile? No, we said that 2.5 weeks ago, 3 weeks ago. Sulfate will never attack anything. We said F minus will never attack anything. Okay? So you have, but these things will act as bases, or water will act as base. Some weak base will take the H and put in the double bond, and now when we assess it, water has been removed. And so we call it an elimination reaction. But it's an E1. But see, on the other hand, if we take the same alcohol and treat it with HI, you'll probably get a substitution product, where ultimately the OH has been replaced with an I. It's the same carbocation. Protonate ionize make carbocation, but I minus loves to attack carbocations. It loves to act as a nucleophile and make a bond to carbon. And so, ultimately, better nucleophiles give you substitution products. Bad nucleophiles, you end up getting elimination products.
So is it H2SO4 a catalyst in the first reaction? Because is it reformed by taking, does it take the H plus in order?
Yeah, you're gonna, if you do your mechanism, you'll see that up here you've got you get the cation, and by the way, this cation here, well, let's do it first. How do you get final product? H is removed. What can remove H? Well, I would use the anion. take the H and move the electrons in, put the double bond in. Or you could use water. If you use water, you're going to form what? H3O plus. But guess what? That's what that is. How does this exist in water? That's an aqueous acid. That's how it exists, so that's actually strictly more correct. You start with acid, but you also generate acid. Or you can actually generate H2SO4. Yes, it's catalyst, it's reformed. Those are regenerating acid. H3O is an acid. H3O plus is an acid, sulfuric acid. Okay, we've mentioned that story now several times. By the way, this could rearrange. In a mechanism, you could show, instead of this coming in, you could show a hydride shift. And you could show this cation. Then you could eliminate, and something, then it takes this H and this moves in. You get the same product, but you could include a hydride shift in your mechanism. You actually would argue that this is probably favored because this moving internally is probably quicker than this other molecule coming in and taking it. Sort of like, okay, slap my hand, boom, I'm here first. This is going to shift. So, but some books and some, and even some, may just not include the hydride shift. Because you can get the product from here as well. Just take that H. But it's actually strictly more correct to include a hydride shift there. Explain why alcohols cannot be dehydrated by an E2 mechanism. How do you make OH go to leaving group? Propionated with what? Not water. Water's not an acid. Strong acid. Okay, you've got to propionate the OH with a strong acid. But if you've got to have a strong acid, that means you can't have a strong base. Right? And since you can't have a strong base, you cannot dehydrate an alcohol by E2. You can't have strong acid and strong base at the same time. But OH requires a strong acid to propionate it. And so you have to do your elimination under strong acid, so it has to be E1. Right? You have to remember that once you start making carbocations here, by leaving groups leaving, you're doing carbocation chemistry. And remember stuff from back then. Skeletal rearrangements, carbocation rearrangements, yeah? One of your things. This here is actually a dehydration reaction. I mean, we make that plus water. Or you can show that like this. A lot of times we just say, hey, we're eliminating water there. That's what, if you look at the formula of the two, starting in the product, we've removed water. So that is a dehydration reaction. But a little bit more has gone on there. That's because carbocations are prone to doing things. There's a mechanism you can try on your own. Okay? Keeping in mind, if you're doing carbocation chemistry, what can carbocations do? Now we've already kind of said this, but we'll kind of say it in a different way. We're looking at elimination versus substitution, right? A more sterically hindered base will favor elimination over substitution. For example, if you wanted to convert this to this, which reactant would you use, a reagent of these three? Which would you use? First of all, what type of reaction do we want to perform here, accomplish? Yeah, we want to eliminate. Okay. All three of those bases could potentially eliminate. They're all bases. Which one would be best?
The last one
Why the last one?
is big, so it'd be sterically hindered. Should be a third
Why is sterically hindered good here?
So you want to create the complement.
There's no regioisomers possible here. The only way you're going to put double bond is here. There's only one beta hydrogen. There's no beta hydrogen here. So we don't have to worry about Seth and Hofmann. Why do we want to use the base on the end?
Well, wants to do a substitute.
This is where we're looking at substitution versus elimination. If you use ammonia, it could maybe take the H, but what else could it do?
Take all the,
Oh, or maybe it could do this. Couldn't ammonia do an SN2? Yeah. We don't want to be SN2. So how can we keep the SN2 from happening? What affects SN2 a lot? Sterics. Less likely to do SN2. All right. Everybody with me? G, clever ways to make ionization of an alkyl halide to a carbocation faster. Usually in alkyl halide, we don't do anything to the leaving group. It's a good leaving group, good to go. Don't have to protonate or anything. But you can make it a positive a different way by treating it with a Lewis acid. In this case, silver ion, Ag+. That's the main thing here, the cation, silver. What type of reaction are we doing here? This looks like an elimination, right? We're eliminating HBr essentially. Okay, is it E1 or E2? Obviously it's E1. Why is it E1? Do we have a strong base? Nitrate here is not a strong base. That's the anion of a strong acid. Nitric acid is a strong acid. That means the conjugate base. Nitrate would be a weak base. Indeed it is. Yeah. Nitrate is going to be like sulfate, not a strong base. This is an E1. What's the first step of the mechanism? Forget about the silver nitrate. What's the first step? Leaving group leaves. That can be a little slow sometimes. This is going to make a secondary carbocation. It would be easier if it was tertiary. Secondary is going to be a little slower. Primary we would never do. Maybe a little slow to ionize. Do we have a clever way to make ionization of the alkyl bromide faster? Yes, we can include silver ion. Silver nitrate being most common because, as we learned in Gen Chem, about solubility, what do you know about nitrates? Are they soluble in water? Yes, that's right. All nitrates are soluble in water, right? We learned that in Gen Chem solubility rules? Okay, does that sound right? You didn't learn solubility rules? Okay. I think all nitrates are soluble. Are all sulfates soluble? No, lead sulfate is not soluble. Lead nitrate is soluble. Remember all that stuff? Okay. So that's why we're using silver nitrate, because what about silver bromide? Is that soluble? No. Remember silver halides? They're not soluble? Okay. So it's a soluble source of silver ion. What happens here? By the way, what's this definition of a Lewis acid?
Accepts electrons.
Yes. Accepts electrons. Well, here you go. It's about to accept them. You ready? Bam, it just accepted the electrons from bromine. It's Lewis acid. What does that give? We're making a bond to silver, and that is bond to silver. Is this possible? How many lone pairs here? 2. Charge of bromine now. Positive. In the end, this is a way to make a halogen positive, complexing with silver ion, which is a Lewis acid. Now the bromine is going to be more eager to leave. It's like, okay, I got to have some electrons. Sorry, carbon, I'm taking the electrons and I'm leaving. And when it does that, what does it give? It gives you your carbocation that we want, right? Plus what? And what do we know about silver bromide in terms of its solubility? Precipitates, right? Yeah. Now that's similar to how do we make oxygen a better leaving group? Make it positive. We made the bromine positive, or chlorine. But with oxygen, you make it positive by reacting with a, what we call a Bronsted-Lowry acid, proton. See, with halogens, for some reason, they just don't respond to acid. You can't protonate a halogen like that. But they will complex with silver ion and a few others. And it may be, the reason this works is because the silver precipitates and that drives the equilibrium. When this forms a precipitate, it pulls the equilibrium that way and it makes things work. Solubility rules? I'm serious when I ask this. Did y'all cover solubility rules in Gen Chem?
Yes.
Yeah?
Yeah.
Here?
Yes.
Okay. Do you remember silver halides being not soluble? And that's like with photography and silver and stuff, and how do you make silver ion soluble and stuff like that? Anybody develop their own photographs or anything? If you do some of that, you'll use chemicals that manipulate the solubility of your silver ions. Okay. Okay. So Lewis acid, accepting, yeah, we see the use of the Lewis acid. So it's not a Bronsted-Lowry acid, that's an H. This silver can be used as a chemical test. We can test for the presence of ionizable halogen. Which compounds below we give a positive silver nitrate test? The positive being the precipitate of silver halide being formed, which you can see. Which one should form silver halide? The bromine's only going to leave if it's going to make a reasonable carbocation. I mean, even if the silver's around, if you can't make a big reasonable carbocation, even the silver won't make the bromine leave. Which one of these can you make a reasonable carbocation? That's really the question. Well, these three.
We're gonna make, is this bromine gonna leave?
No.
You're gonna make carbocation on that carbon?
No, it's not a tetrahedral carbon. You can treat this with silver bromide and you're not, with silver nitrate, and you're not gonna form any silver bromide. So you won't get a precipitate there. With the other three, you will. Question, which of those three over there would give the silver bromide the fastest?
7.
It's basically asking you which one's going to form carbocation the fastest. And basically that question is asking you which one is going to make the best carbocation. Because that would be the fastest to form. Everybody got it? Caitlin?
You have them right there, right?
Okay, number 2. What are we under? One was what? How to make
Really fast.
how to make carbocation easier, faster, alkyl halides. Another way is to use a polar solvent. If we look at this reaction here, if you take this alkyl bromide with this alcohol and maybe heating it, and some type of polar solvent such as acetonitrile or DMSO, we can get a substitution reaction. Under my hand used to be bromine, but now it's the oxygen. The alcohol, of course, this remains bonded to the oxygen here, right? Bromine, oxygen, bromine. Substitution reaction. On the other hand, if you use a solvent such as hexane, nonpolar, probably not going to get a reaction. Why does a polar solvent help this? Well, what's the mechanism here? It's a substitution, SN1 or SN2?
SN2.
SN1 or SN2? Why is it SN2?
Can't let oxygen just pop off the
This should be quicker, guys. Why is it SN2?
Oh, yeah.
Why is it SN2?
You reform HBr, which is a strong acid, and so.
No, that has.
The solvent is.
What do you mean reform?
Catalyst.
There's no we didn't start with HBr. We formed HBr. Yeah, I agree with that, but it has nothing to do with is it SN1 or SN2.
Because the solvent is abiotic. DMSO.
No, it's SN2 because there's no strong nucleophile. SN2 requires strong nucleophile, right? We looked at how to determine weak versus strong nucleophiles. Okay. Do we have a strong nucleophile? No, it's SN1. There's no strong nucleophile, right? All right. And since it's SN1, what's the first step of the mechanism? Leaving group leaving? And what we're looking at is clever ways to make the leaving group leaving easier. That's the letter we're under. How do we make the leaving group leave easier? We use a polar solvent. Acetonitrile, these are probably both on the solvent list I gave you, is CH3 and then the cyano group. And DMSO is similar to acetone, except that's sulfur instead of carbon.
Dimethyl sulfoxide. Both of these are considered polar, non-nucleophilic solvents, for the most part. Polar, they're considered aprotic. Whereas alcohol would be considered protic. That leaving to make this polar solvent is going to facilitate that because we're making ions. Polar solvent will give the ions some love. What if we were doing this in hexane? Will hexane give these ions any love? No. What happens when you put HBr in water? A polar solvent. It ionizes. It makes ions. I mean, you can show H3O plus, Br minus, or just H plus. It makes ions. What happens if you put HBr in hexane? Gen Chem, right? What happens if you put HBr in hexane or nonpolar solvent? Nothing. It remains covalent. Because hexane will not give the ions any love, and so it's not going to form any ions. Ions are formed when whatever is around the solvents can coordinate and give IMF. So this is a favorable thing. It promotes ionization. Polar solvents promote ionization. Nonpolar solvents do not promote ionization. This is going to be very difficult to ionize down here because the solvent doesn't give the ions any love. All right? Polar solvents help ionization. Deuterium isotope effect. And we're getting to near the end of this handout here. And we can maybe look at that. Possibly today, but with a few minutes left today, maybe I can see if we have any questions about anything, including some of the questions in the substitution handout. I sent the key over the weekend. Is there anything there? We'll finish this handout up, finish this up tomorrow after our quiz. Summing it up, what type of nucleophile can participate in an SN2 reaction? Strong. But only strong. Only strong. Right? Because strong nucleophiles are also bullies. They're gonna stick their nose in there. Here I come. I'm not waiting on you to ionize. Here I come backside. Boom, kick you off. The weak nucleophile will not do that. And thus, the only thing that can happen is the ionization. So the questions at the back here, anybody have any questions about the questions? Back here, I sent the answers. Any questions? These below here. How are we doing these here? Meth, how'd you do on synthesizing meth? And mechanism there at the bottom? Uh-huh.
For the next one, with the mechanism that's involved, would it be SN1 since you would have to have a strong acid of some sort?
Mechanism for what reaction?
The medical one, the one thoughts.
Yeah, but what reaction? Just one reaction?
No, I had like steps.
Which step are you talking about?
Oh, I just meant the like whole thing.
No, I mean, two steps would be two different reactions. I assume that's what you mean by two steps.
I was thinking it, I guess it's like two different reactions, but like.
You just kind of see what you have.
I just like, I put the one step next to the other. I didn't draw out like the mechanism.
Well, I'm not, you don't need a mechanism. The question is not asking you to show mechanism, the question is asking you to provide reagents. More than one step will be required. See some of you this afternoon at 2:30. Have a good day, guys.